Hi guys, welcome back to this series of which I'll be discussing IMONST problems. These are sample problems though, and this will be the last video in which I'll discuss 3 problems. The following 2 will only involve 2 problems each because they are getting progressively harder, we need to admit that. So in this video we'll be discussing problem 14, 15 and the next one is 16 in the next page. So let's take a look at question 14 first. Question 14 will need some, observations. And then maybe you can't observe that, I don't know, but try to do it yourself first. Some positive integers have sum 22, so what is the maximum possible product of these integers? You can pause the video here, but I'll be showing a step-by-step guide. I don't know if it's really step-by-step, but I'll try my best to explain from my point of view. So think of it like this. We won't count 22 first because 22 is too big of a number, right? So we'll do, maybe say some positive numbers have sum 8. So maybe say a plus b plus c plus blah 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 equals to 8. What is the maximum possible product of these integers? So if we say maybe we just retain the 8 and then maybe we say this one we do it as 4 plus 4. So which one will be bigger? 8 itself is just 8, so we don't see any changes, and then 4 plus 4, and then we'll see 16, so this is obviously bigger. So what about 7 plus 1? 7 times 1 is 7, but wow, this is actually smaller than 8. Then what about 6 plus 1 plus 1? This is 6, that's smaller. So here we can make our first conclusion, which is to break up into smaller numbers. But not 1, because if you break it up into a lot of ones, they will still be the same product. There won't be any, growth. There won't be any increase for the total product. So this is our first step to be aware of. And then maybe say for the second step that I would like to explain. So maybe say we don't say 8, maybe we say 15. So for some obvious reasons I'll be explaining later. Maybe we can divide this, so we know that we need to divide the number but not into 1. So maybe we say we can divide it into 5 times maybe 5 plus 5 plus 5, and then this one maybe I will divide it into 3 plus 3 plus 3 plus 3 plus 3. And then another example would be 6, because this one is a very crucial one, to be honest. Maybe I can divide it into 3 plus 3. Maybe I can divide it into 2 plus 2 plus 2. So for this 5 plus 5 plus 5, its products will be 125, and then for these 5 3s, its product will be 243. So obviously this one wins. And then 46 over here, so we have 3 times 3 equals to 9, and 2 to the power of 3 equals to 8. So this 9 wins. So the second observation we have noticed from here is that it is best to break up into 2s and 3s, because because you can get the most number of pieces, and then the product will be maximal. Okay, and then if we are not sure of whether we should break up a number into how many 2s or how many 3s, for every 6, because 6 is a multiple of 2 and 3, for every 6 we will have what? Optimally, so at best break into 2 3s. Okay, I hope you get a idea of what I'm writing over here. So optimally break it into 2 3s. So here we have 22. So 22, how many 6s can we divide it into? So maybe we have 6 plus 6 plus 6 plus 4. And so these we'll need to use it first. We can divide this into 3 to the power of 6 equals to 729. And then how do we divide this 4? Actually, you can see, maybe you can do it into 3 plus 1, but this one has a 1, so out. Then we have a 2 plus 2. Then we retain the 4 itself. But 2 times 2 is also 4, so 729 and 4. We just multiply these two together, so we will get our answer as 2916. This is the answer, but I would like to share some general ways of tackling such kinds of problems, although they are rare. They are a rare sight to behold. So for this kind of problems, if sum is multiple of 3, is multiple of 3, break up into all 3's. Okay, so this is 1. And then secondly, if sum is in the form 3x plus 1, so x being a positive integer, so means this number, the sum when divided by 3 has a remainder of 1, break into several, I don't know how many, 3's and 2's in the end, because 2 times 2 is 4. You don't want to have any 1's appearing inside. So this is the second one. And then for the third one, if sum is in the form 3x plus 2. So how do we break this into? Break into several 3's and 1, 2. So 3 to the power of something times a 2. We will get the maximum sum. So this is what we've observed. And this is our very lengthy solution to the problem. So give me a few minutes to pause. I will need to erase this. Okay, so I finally erased a lot of stuff. So here we will have problem 15. So this one is also geometry, so also don't get daunted by it. It's actually quite easy if you can make these observations. So I'll be drawing as I speak. In a triangle PQR, angle PQR, so it's this one, is equals to angle PRQ, so it's this one. So both of them are equal to 70 degrees. Okay? So if we see two angles of the same size, this means that this one is equal to this one. Okay? And points S and T are on the sides PQ and PR respectively, meaning point S is somewhere here, point T is somewhere here, such that angle RQT equals to 55. So this is T right over here, and then our angle RQT is 55. And angle QRS, so somewhere over here, is 40 degrees. So this is our S. And find angle PST in degrees. Yes, this is a very daunting question to look at first, but try and calculate the angles and you might get a much better insight. So for this triangle TQR, so we know this one is 70, this one is 55, so minus it, we will get angle QTR to be of 55 degrees. And we see that this one is 55 and this one is 55. So what does this mean? This means that this is also an isosceles triangle. QR is equal to RT. So this whole length is actually for PR. Do not get confused. And for the triangle QRS, so we have 70 over here, 40 over here. Then minus it, we will also get a 70 over here. So this also means that this QRS is also an isosceles triangle. QR is equal to RS. And you can see that QR is equal to SR is equals to TR. Okay? So this also means that this STR is also an isosceles triangle. And to find the angle PST in degrees, what we need to do is to, how do I say? So we already know this is 70, we need to know this one, so we also need to know this one first because these three add up to be 180. And then this one is actually quite easily known, but we need to know this one first because this one is also 80, and then this is 100, this add up to 180, and these two are of the same magnitude because this is an isosceles triangle. Triangle SRT is an isosceles triangle, remember that. And so we find angle SRT to be, okay, 70 degrees minus 40 equals to 30, and then this 180 divided by 180 minus 30 is 150, and then divide by 2. We have RST is equal to RTS is equal to 75 degrees. Maybe I write here 75 degrees. This is also 75 degrees. So we know that this PST plus 75 degrees plus 70 degrees is equals to 180 degrees, and do some subtractions, and you will get that angle PST is equal to 35 degrees. So this is our answer for problem 15. Jot it down. Whew. Okay, we will. Okay, so this is our last question of this video. Yeah, this one will take quite a long time. A triangle has sides of length 11, 15, k, where k is an integer. For how many values of k is the triangle obtuse? An obtuse triangle has one interior angle greater than 90 degrees. So to give you a brief understanding, there are three kinds of triangles. So this one is called the acute triangle. Acute triangle meaning that all angles are less than 90 degrees. And then we have a right angled triangle where one of them is exactly 90 degrees. And then we also have this obtuse triangle, which is what we are needing to find, where one of them is equal to, or should I say, larger than 90 degrees. Yeah, so we need to find these kinds. But this one will actually give us a good, this one will actually give us a good view of what kinds of triangles will be there. So actually we should build up from here first, okay? So, and remember the triangle inequality. Triangle inequality, so I'm just using short form, where a plus b is larger than c, okay? So we maybe say k and 11 are the shorter sides, and then 15 is the larger side. So this means that k will be larger than 4, okay? So k minimum is 5. From here, noted from here. And then maybe say k is the largest. So maybe say in the second case, k is the largest one. So k is smaller than 11 plus 15. So k maximum is 25. So our k ranges from 5 to 25. So jot it down. I'll be erasing this one to make some space. Just remember the triangle inequality here, and then we'll also be using right triangles to find our solution. So give me a moment. Oh my god, why am I doing this all in one go? Oh. Okay, so for right triangles, we will have two kinds of cases. One of them is where 15 is the longest side, and then we have 11, and then there's k. And then the other case will be where k is the longest side, and then 11 and then 15. So because we just said that k can range anywhere from 5 to 25, right? So maybe say if we cut k a little bit shorter, so we cut k a little bit shorter, something like that, and then we will see that there will be an obtuse triangle forming. And then in this triangle, in this right triangle, if we extend k by a little bit longer, so this one is still 11. So we'll also see obtuse triangles forming. So yeah, so we need to find these two k's. What are their values? So assume this is a right triangle. So by the Pythagorean theorem, so in case you don't know Pythagorean theorem, you can search it on the web, but I just tell you that a squared equals to b squared plus a squared plus b squared equals to c squared. C is the hypotenuse, namely the longest side in the triangle. Okay. So I'll be using this one, and so here k is one of the shorter side, so k squared plus 11 squared, k squared plus 11 squared equals to 15 squared, and then k is equals to I already did myself, so it's equal to square root 104 is around 10.2 something. So here we will want our k to be smaller than 10 for an obtuse triangle to form. So this is one case. And then here we assume k is the longest side, so k equals to square root 11 squared plus 15 squared is square root 346 is somewhere between 18.6, something like that. So our k needs to be larger than 18. Okay, so we will have these two values of these two kinds of k. One is k smaller than 10, one is k larger than 18. So we will have 5, 6, 7, 8, 9. Actually, smaller than 10.4, should I say, then larger than 18.6, something like that, to be more exact. Okay, 10. So this is for the first batch, this one. And then for the second batch, we will have this one bigger than 18.6 will be 19, 20, 21, 22, or until 25. So just count how many cases are there over here. And if you are still skeptical of why I did this, maybe you can try experimenting yourself. So here we have 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So problem 16, we will have 13 cases. Okay, so here are our answers, and I think we have just finished discussing 3 problems. Wow, that was a very long journey. Okay, so in the next 2 videos, we'll only be discussing 2 problems. So yeah, so see you in the next video, and bye bye.